All the light and heat from the sun have their origin in hydrogen, a natural fuel that is the most abundant element in the universe. Hydrogen is the fuel of life. Scientists and technical experts are studying hydrogen very closely. Some believe there may come a day when nobody has to worry about energy. "75% of the universe is made up of hydrogen. On the Earth, however, the percentage is much lower. A large share of all the atomic hydrogen and molecular hydrogen that probably existed here once upon a time drifted off into outer space. The rest makes up an important percentage of our planet's water and organic substances. Hydrogen's potential as an energy source resides in its capacity to bond with oxygen to form water. Though it may seem strange, this is not so different from the process of burning fossil fuels or biomass. The energy potential, however, is much greater. The same amount of hydrogen could generate 3 times more energy than natural gas or gasoline, for example, and 5 times more than coal. We know of no fuel, in fact, that is more efficient than hydrogen. Also, you don't have to burn it to use it. These are fuel cells. They're designed to generate electricity at normal environmental temperatures. They work by bonding hydrogen to oxygen by means of a catalytic membrane. In Japan, the US, or Europe, the first commercial fuel cell-equipped vehicles are already running. They're similar to gasoline-powered vehicles and offer many intriguing advantages. They don't pollute, they don't make noise, and they run on an endless source of energy. The only drawback is that current hydrogen technology is still very primitive. Almost all the hydrogen that exists on Earth is in water or organic compounds, and splitting the hydrogen atom is still very expensive. Right now, hydrogen as a source of energy is limited to certain special applications such as space exploration. In order to harness the potential of hydrogen on a practical level, scientists will have to first answer a few difficult questions. For example, liquid hydrogen is extremely flammable and therefore dangerous to handle. Also, fuel cell catalysts are made of platinum, which is a very rare and very expensive metal. The total amount of platinum in the world could not even replace a fraction of the cars currently running on our roads. Nevertheless, forecasts are fairly optimistic. Some experts believe that hydrogen will soon be used much like the way we use gasoline today. They say that in a few years, we might very well be able to produce viable energy from water. We might produce it at solar energy power plants, and the big automakers may find an alternative for platinum. On July 16, 1945, the first atomic bomb was detonated in Trinity, New Mexico. 1 gram of plutonium was enough to generate 12.5 kilotons of destructive power, the equivalent of 12,500 tons of dynamite. As has happened so often in history, military science was one giant step ahead of civil society. The atomic bombs dropped in the Second World War were based on nuclear fission. A neutron bombards a heavy nucleus, such as the nucleus of uranium or plutonium, and the nucleus splits into 2 lighter nuclei. The collision releases new neutrons that bombard the new nuclei. This becomes a chain reaction and releases tremendous amounts of energy. This process of nuclear fission is the same one that today produces 17% of all the energy consumed on Earth. If we had to resort to burning fossil fuel for this same amount of energy, we would unleash 700 million more tons of carbon dioxide into the atmosphere than we already do on a yearly basis. Roughly the same amount spewed out by the 200 million or so vehicles in the European Union countries. The general public, however, still thinks of nuclear energy as more dangerous than advantageous. The terrible accidents that have occurred at 3 Mile Island and Chernobyl are not easy to forget, even if modern nuclear power plants are much safer. Of course, the future of nuclear energy does not depend just on safety. Like any other industrial activity, the generation of energy from nuclear fission produces contaminating residues as well. In this particular case, the waste products are extremely dangerous, and we still don't know how to best handle them. Nuclear fission produces byproducts that contain varying percentages of radioactivity. Some of those materials will continue to be radioactive for several hundred, thousand, or even hundreds of thousands of years. Some countries, such as the United States, Finland, and Sweden, are still studying ways to safely store these residues in underground sites, but completely acceptable solutions have proved to be quite elusive indeed. Nuclear energy does not contribute to the alarming changes in the Earth's climate, but neither is it as clean as it might seem. We've built much safer nuclear reactors and developed increasingly sophisticated materials and installations, but we still don't know what to do with our nuclear waste. Maybe someday in the future we'll have no choice but to build nuclear waste dumps far away from planet Earth. However, right now, that's still the stuff of science fiction.
The hottest thing that's happening now has to do with fuel cycles. As I said, we're looking for greater efficiency. It is accepted that you can burn fuels that have already been used in light water reactors, and you can burn oxides mixed with uranium, plutonium, or thorium. This means that in the new fuel cycle reactors, you have the advantage of burning fuels that you already have, meaning that you save money because you're not spending it on storage. All these processes are still very complicated and not firmly established. They are thinking very seriously about exactly how to evaluate how much a nuclear power plant really costs. We can burn fossil fuels. There's still plenty out there. When you take a combustible element from a light water reactor, the problem is that you have lots of energy there. The problem isn't that you have residue. The problem is that you have an element that can still produce a lot of energy. So, in that sense, the costs of storage can be transferred in reality to a decrease, because you're never going to spend that on storage. Rather, you're going to take advantage of it and generate more energy. So all of these new fuel cycles are what require more analysis, because they imply, without a doubt, the advent of new technologies. And that's where the most work is being done right now.
Or perhaps the answer lies not in splitting atoms, but in joining them. Instead of fission, fusion. For while fission tends to break things up, fusion brings things together.